One more example of an expected value problem, it can be done with a lottery ticket. There's lots of different lottery tickets, lots of different prices on lottery tickets that are out there. I don't typically play the lottery or buy lottery tickets, but I've received them as gifts, and so I've kind of looked at them a little bit, not much, but and you can find probabilities and stuff online for different lotteries. But here's one that I just made up, hypothetical. Let's say you were to buy tickets for $1, so they're $1 a piece, and there's 2 million tickets available for this particular lottery, or 2 million players or something. And let's say you look at the back of the card and it says you're going to have 100 of those tickets are going to win $2,000, 20 of them will win $10,000, and 2 of them will win the jackpot, which is $500,000. Like, wow, $500,000, I could be a big winner. Okay, well, that's true. Don't forget though, there's a lot of people who are going to be losing $1 basically. And so an expected value problem is not what you can expect on a particular on a particular play or on a particular ticket. It's what you can expect as an average in the long run. So if you were to play this 1,000,000 times or even 1,000 times, what the average win-loss, how your wins and losses would average out over time. Okay, so that's an expected value. So we can do that again. When you calculate an expected value, you take the value of the outcome, multiply it by its probability, and then add those products together. So in this particular case, you have a 100 out of 2 million chance or probability of winning $2,000. So let's set this up. First of all, in a table, we'll do the outcome, the probability, and the product. Okay, so I like to have these 3 columns kind of set up. The outcome obviously is, and we'll go in order maybe from greatest to smallest here. So you have the $500,000 outcome. You have the $10,000 outcome. You have the $2,000 outcome, and you have a -$1 outcome, right? Which is going to play into this pretty significantly. So those are your main options, right? You can either lose $1, you can win 2,000, win 10,000, or win 500,000. Now the probabilities are based upon the number of winning tickets out of 2 million. Okay, so the probability of getting 500,000 is going to be 2 out of 2 million. The probability of getting $10,000 is 20 out of 2 million. The probability of getting $2,000 would be 100 out of 2 million. And the probability of getting a -1 or losing is all the rest of them. So you got to figure out what all the rest of them are. And so all the rest of them are going to be 2 million tickets minus the sum of those, which is 122. Okay, so it's a lot. It's 1,999,000. What's that? 818, I believe. Carrying in my head. No. Yeah, that should work. Take 122 off of 1,000, you get 818. So, no, not 818. That's not right. 878. Did I do that wrong? I did. The carrying is terrible. That's a 10. That's a 9. That's a 9. 878. Yeah, okay, that's right. 878. Got it. Anyway, so that's the that's the number of losing tickets. A lot. And so you have 1,999,878 out of 2 million chances of having a -1. Okay, so now you calculate those products, And I'm just gonna put that in the calculator because yikes, some of these are pretty ugly, but some of these reduce nicely. I'm not gonna bother with it. I'm just gonna go through the calculations. So I'm gonna type in, there's a lot of zeros to keep track of here, so bear with me. It's 500,000 times 2 divided by 2 million. 1, 2, 3, 4, 5, 6. That's 0.5. Okay, so that product is 0.5. Here, this is 10,000 times 20 divided by 2 million. 2, 0, 0, 0, 0, 0, 0. That's 0.1. This one is 2,000 times 100 divided by 2 million. 1, 2, 3, 4, 5, 6. Yep, that's right. That's 0.1 also. And then finally, we do -1 times that number, 1,999,878 divided by 2 million is negative 0.999939. There it is. Good. So now our actual expected value, and typically we use the letter E to represent the expected value, is simply the sum of those four numbers. So I take that last number and I add 0.1, add 0.1, add 0.5. And I'm going to get negative 0.299939. All right. And so what that means is if you round that a little bit to the nearest penny, you can expect to lose 30 cents per ticket. Okay, so if you played this 1,000 times, you would expect to lose $300 total, even if you won the jackpot, right? So no matter how many times you play this, in the long run, the average gain or loss will be, in this case, a loss of 30 cents. Okay, overall per ticket, right? So that's an expected loss of 30 cents per ticket in the long run. Now, obviously, if you just play it one time, you really could win any of these, right? And then this expected value thing is just kind of, it doesn't really average out after 1 or 2 or 3 plays, right? But if you played it 100 times, would you lose $30? Even then, you probably win one of these. You might win one of these once or something, or maybe you lose all $100. But you played 1,000 times, could you lose? Would you lose $30 or $300? If you played it 1,000,000 times, you would, on average, lose $300,000. Okay, so the more you play this, the more the likelihood is that you're actually going to lose. Okay, a lot of people would think the more they play, the more likely they are to win. But in reality, the more you play, the more likely you are to reach this average, or approach this average of a loss of 30 cents per play or per ticket. So it actually doesn't benefit you in the long run, because even if you win the jackpot, you've lost so much that you can't recoup that much money. Okay, so, and the odds of winning the jackpot are pretty small anyway. So so basically, this is why I don't typically play the lottery, because I understand the expected values, and that the odds are never actually in your favor. To kind of somewhat quote one of my favorite movies, Hunger Games, there, the odds are not really in your favor in these. Same thing with casino games. You go to a casino, and the slot machines and a lot of those games, even craps and what's the one, roulette with the spinning wheel, those are all the expected value of all those games, if you actually calculate them, are always in the negative for the player, always. Okay, they would never even make a game where the expected value could be in the positive because they'd be guaranteed to lose money over the long run. And so the casino, that is. And so anytime you play at a casino, unless you're playing like blackjack or poker where there's actually like some skill involved, you can increase your odds a little bit by being good at it, somewhat good at it. But if you go to a casino and you're just playing games of chance, they always in the long run work out to be a loss for you. Same thing with lottery tickets. You're in the long run, you're going to lose money, not win it. And so the more you play, it's actually the case that you increase your chances of losing, not winning, in the long run.